Now, continuing section 4, we'll talk about SI units. The System International, or International System. It's French. Remember, America is not the whole world. SI is the standard set of units used pretty much everywhere in the entire world, so that everyone always knows what everyone else is talking about. The United States kind of remains the lone exception to this. We still use the old imperial system, 12 inches to the foot, 5,280 feet to the mile, 16 ounces to the pound, all that garbage stuff. And the reasons are just because the U.S. is rich and powerful, and we can get away with it. That's really all there is to it. But when it comes to science, we do use the international system. And thank goodness for that. The international system is so much more sensible. First off, we have the base units. These are the fundamental physical properties, sort of like the elements of measurement. Mass is measured in grams or kilograms, things like that. Volume, depending on the scale you're working at, will be measured in cubic meters, cubic centimeters, liters, milliliters. In chemistry, we tend to work a lot in liters and milliliters. Okay? 1 milliliter is 1/1000th of a liter. We'll be getting into prefixes soon, don't worry. And 1 milliliter is the same as a cubic centimeter. That is a unit of volume about the same as, again, the tip of your pinky finger. 1 liter is equal to 1 cubic decimeter. Okay? There are 1,000 milliliters in a liter. There are 1,000 cubic centimeters in a cubic decimeter. One of the advantages of the international system is that it's made conversions so much simpler. Don't worry, you'll have to practice these a bit, but you'll see that they're very easy, especially compared to the imperial system. Next up, we have time. Now, time is one of the things that the international system wasn't able to simplify, but that's just because we live on a stupid planet orbiting a stupid sun that didn't have the decency to come in units of 10. But the base unit of time is the second, and that should be pretty familiar, especially since it still says 60 seconds to the minute, 60 minutes to the hour, and so on. Next up, we have distance, measured in meters. You'll see that the meter is the same meter that's used in volume. That's okay. We're cool with that. Temperature is a weird one. It is measured in either kelvins or degrees Celsius. Depending on the situation you're looking at, you might be able to get away with using Celsius. That's not a problem. Sometimes, though, you'll absolutely have to use Kelvin. And you're going to want to be familiar with how to convert from Celsius to Kelvin. They work at the same scale, but Kelvin's just higher. Kelvin is degrees Celsius plus 273.15. Celsius is based on water, where 0 degrees Celsius is the freezing point of water at standard pressure, 1 atmosphere, sea level, and 100 degrees Celsius is the boiling point of water at sea level. Kelvin is an absolute temperature scale. There's really no such thing as a negative temperature, because temperature measures the motion of matter, the random movement of particles due to heat. As something gets hotter, the particles move faster, and that's its higher temperature. So as you cool something down, it slows down, and it would eventually stop. You can't have a negative average motion, so you can't really actually have a negative temperature. And sometimes it's very, very important to keep that in mind, and in those cases, you have to use Kelvin. You'll never get it wrong sticking with Kelvin all the time, but sometimes it's okay to stick with Celsius. Next up, we have electric current, amperes, amps. That will pretty much never show up in chemistry. In second semester, we do fool around with batteries. We talk about electrochemistry, but we don't worry too much about actually setting up circuits and so on. That's more physics. This next one, though, the amount of substance, that is a big deal in chemistry. You will become familiar with the mole. You will work with it a lot. The amount of substance is not the same thing as the amount of mass. Remember, mass is the amount of matter. But as we'll see later, atoms can have different amounts of mass. Moles tells you how many atoms you have, not how much mass you have. That's going to be another important distinction. And finally, luminous intensity, the measure of the brightness of light, measured in candelas. We don't worry about that at all in chemistry. Well, at least not in these first 2 semesters. But we wouldn't get very far if we limited ourselves to base units. We also work in derived units. We can combine units to talk about different kinds of properties. When you add 2 units together, then you're dealing with the same kind of unit, the same kind of measurement. But when you multiply or divide, that's when you get derived units, and you're measuring different physical properties. Length times length gets you area. Length times length times length gets you volume. Mass divided by volume gets you density. Length divided by time is speed. Mass times length divided by time divided by time divided by time is power. Okay, so derived units can appear incredibly complicated. But if you sort of follow along how we get from step to step to step, how we can build up to those derived units, then they will eventually make sense. Such that power is actually energy divided by time. How much energy is transferred from one place to another every second. Energy is force applied over a distance. So you push on something for a certain length of distance, and that's a measure of energy. And then force is mass times acceleration. So a force is how hard you have to push on something or pull on something in order to get it to change its velocity, being speed or direction. That's acceleration. You can build up these apparently really ridiculously weird combinations of units to get these derived units, but you can break them down and they'll make sense. The important thing is to work your way up to them and not to start with something weird like power. Another thing, something you have already noticed, something we've alluded to a few times, is the prefixes in the international system. We use those because the scale of things is inconvenient. Okay? The universe was not set up with human beings in mind. The universe is 432 quintillion, 339 quadrillion, 120 trillion seconds old. And a hydrogen nucleus is 1,756.6 quintillionths of a meter across. Those numbers are just kind of crap. I mean, look at all those zeros. Those zeros are only there to tell us the size of the number. We can use prefixes instead. Not only will the prefix still tell us the size of the number, but it'll get rid of all those zeros. It makes it a heck of a lot easier to write those numbers. Okay, so that's what SI uses prefixes for. SI changes the scale of things. It's a way of telling you about the magnitude of the measurement. And it makes things a lot easier, right? I mean, seriously. I mean, counting those zeros was a huge pain in the ass. I edited it out of the video to make things go a little bit faster, but it was annoying. Okay, prefixes make it a lot better. So some prefixes make the units bigger, which makes us able to write smaller numbers. Other prefixes make things smaller. Okay, so tera, a capital T, indicates a trillion of something. 1 terameter is 1 trillion meters. A giga is a billion. Mega is a million. Kilo is 1,000. Heka is 100. Deca is a 10. There are 7 gigapersons roughly on the planet, 7 billion people. Whereas there are 300 mega people, so 330 mega people in the US, 330 million people. On the other hand, it's about 5 kilometers from my apartment to the school I work at right now. Heka and Deca are far more uncommon, but not unheard of. And that dashed line, that's just where you'd find the basic unit. That's the 1, where you don't need a prefix. So 1 gram would just be a gram. But you could say 10 grams is a decagram, 100 grams is a hecagram, 1,000 grams is a kilogram. Here we have the smaller prefixes. Deci, for 1/10, centi for 1/100th, milli for 1/1000th, micro, nano, and pico for millionths, billionths, and trillionths. So you've already seen deci. I talked about how 1 liter is 1 cubic decimeter. Centi should be fairly familiar. 1 centimeter, there are 100 of those in a meter, because a centimeter is 1/100th of a meter. Milli, that's getting fairly small, 1/1000th. Micro, you would have already heard of microwaves. Those are real things, not just the microwave oven, but actual electromagnetic radiation, light. That is really weird looking. That is the Greek letter mu, spelled mu. And the way you do that, you just draw the letter U as normal, then you put another straight line coming down from the left-hand side. That's how you do a micro. Be careful, it's easy to confuse a micro with a capital M if you're writing a little bit too fast. I know I always try to be careful about that. Nano, you will have heard of nanotech, of course, 1/1 billionth, and pico, 1/1 trillionth. So, like I said, when you start getting closer to 1, the prefixes become fairly rare. It's just not useful to be able to talk about 10 of something or 1/10 of something for the most part. So deca, hecca, deci, and centi are pretty uncommon. I mean, there are exceptions where you still find them. Deca, you still see in the word decade, 10 years, 10 of a thing. Hecca is almost unheard of, but you still see it in hectare. It's an archaic measure of area from the French Revolution, of all things, that who knows why, but it's still around in some places. An ares, or an are, was a measure of area, and then 100 of those is a hectare. It's still used in measurements of land, sometimes. Deci doesn't show up very often, like I said, 1 cubic decimeter, or a decibel, a measure of the loudness of sound. And finally, centi, centimeter, that's always going to be around, just because that is really the only unit in the international system that's good at measuring lengths on the human scale. That is to say, the scale of the human body. In Europe, height is typically measured in centimeters. So, like, the average adult male height is about 180 centimeters, 1.8 meters, a little bit less than 6 feet. So, centimeters will never go away. You will occasionally find other units being measured in centi something, but that's fairly uncommon. Nevertheless, those just aren't going to go away. You should know them. For the most part, we stick with the others, and it's really easy to work with those because shifting from one prefix to another just means moving the decimal 3 places. Okay? So 150.5 grams. To change it to kilograms, you just move the decimal 3 places, 0.1505 kilograms. To move it to milligrams, same thing, but in the other direction, 150,500 milligrams. 750 nanometers is 0.75 micrometers, or microns, or it could be 750,000 picometers. So it's really just moving the decimal, hopping it left or right. Remember, bigger units mean smaller numbers. So a micro is bigger than a nano, so that you should expect the number to get smaller. Whereas pico is smaller than nano, so the number should get bigger. So visually, the decimal just hops left or right. Mathematically, you're going to be multiplying or dividing by 1,000. That's what it means. Exact same thing. Okay. So you're going to need to practice with prefixes. You're going to need to be good with these because they show up all the darn time. You're going to want to be good at this. If you're not, you're going to have problems. Because we work with different kinds of prefixes at different scales, and those scales interact with each other. So, for example, we work with nanometers when we're talking about light. But when we're talking about bond lengths, we typically talk in micrometers. And when we talk about human scales, movement measurements, we typically talk in centimeters. You have to be able to convert from one prefix to another. You're going to need to get good at those. You're going to need to memorize these prefixes. And King Henry died drinking chocolate milk isn't going to cut it anymore. You need to know everything from Terra down to Pico. Get used to those, memorize those prefixes, and get good at converting between them. I can provide help in the homework, I can provide some help in class, and there's going to be some problems in the textbook. If you need more practice, Google is your friend. Google practice converting prefixes, and you will find 5,000 web pages that will help you do exactly that. That's it for this section. See you next time.